Howdy students, this is going to be chapter 15 and 16, lesson 2, and our main objectives today are going to be examining concentration curves for common acid-base titrations. So what we're going to be looking at is plotting 6 points for, number 1, a strong acid and a strong base titration. In the future lessons, we're going to be covering plotting curves for weak acid, strong base titration curves, and weak base, strong acid titration curves. You may want to have your calculator handy as we work through these problems. Also, feel free to pause the video anytime in order to calculate ahead of time so that you don't get lost. So in our textbook, this is going to be chapter 15.4, and what we're going to be looking at is a titration curve. So in an acid-base titration, we have two components along with some equipment that we're going to use, but the two components are going to be the titrant, which is, let me go ahead and throw this image up here. The titrant is going to be thrown into the burette. And the titrant is a solution of known concentration, and usually this is a base. And common examples that we're going to see will be NaOH. The analyte is the other component, and the analyte is just what substance is being analyzed. And usually it is an unknown concentration, and we are trying to figure out some sort of information, whether it be pH or concentration of that solution. So when we start to add base, we will drop wise into this flask and we will start to neutralize our solution. So what we're trying to reach is what we call the stoichiometric point, or what we know as the equivalence point, which is at which the H plus concentration and the OH minus concentration are equivalent. When we start to plot these points, different combinations of strong acid, strong base, weak acid, weak base will begin to give us different types of curves. So in this lesson, we are going to plot a titration curve for a strong acid and a strong base. So let's go ahead and look at a basic titration curve, and this is going to be for a strong acid, strong base. Right now, let's look at the y-axis, and what we'll find is that we have a pH range from 7 to 0 here, which is indicative of an acid. And we also have a pH range from, this one's 13, right? We know the pH scale at neutral goes, or excuse me, at 25 degrees goes up to 14, and that's for a base. This measures the pH. On the x-axis, we have volume of NaOH, and really the better description here would be the volume of titrant. As we add titrant, you'll notice that we have our pH starts low, and it will eventually start to rise as we add titrant. We will get to an equivalence point, and for now, let's not really pay attention to the 7 because that can change. But the point at equivalence is roughly halfway between the two vertical components of this chart. So this section here and this section here. And this is a rough estimate, but we can see that any addition of titrant in this region is going to really have a great change in pH. So halfway between those 2 points, we find the equivalence. The one we were just looking at was a strong acid, strong base curve, and you can see this one. I'm going to go ahead and label it on the left. And down here, what we have is a weak acid, strong base curve. And then what you'll notice is that on this curve, we start way up high. So this would be indicating a weak base, strong acid curve. And what we're going to be covering in the next few lessons are the 3 different types of curves. Today, we're going to focus on the one to the left. So the first thing we're going to look at is the net ionic equation for a strong acid, strong base titration curve. The net ionic equation comes from the mixture of a strong acid. I'm going to go ahead and give you an example here of hydrochloric acid plus sodium hydroxide, both of which are strong in nature. They dissociate 100% of the time, and what we form is a neutralization of the chloride in sodium, forms a neutral salt. We'll get into that in a second. And then, of course, the hydrogen and the hydroxide will come together to form H2O. And some people like to write it as HOH, but H2O is the proper substance. So what happens is we have the H plus neutralizing the hydroxide to form water. And the pH is going to be easy to calculate here because it will always turn out to be neutral at 7. One other thing to note is that NaCl is a neutral salt. When you have a strong acid, it will produce a weak conjugate base, and when you have a strong base, it will produce a weak conjugate acid. So neither of these ions will contribute to any sort of rise or fall in the pH. So example 5 begins by saying we have 12.5 milliliters of 0.2 molar HNO3, which is a strong acid, nitric, and it's titrated with 0.100 molar of NaOH, which is a strong base. First thing we want to do is go ahead and look at our experimental setup. So what we're going to have, if we were doing this in a lab setting, we would have the burette set up, and inside here we would have our titrant, which would be 0.100 molar NaOH. Down below, we would have, draw my Erlenmeyer flask, is going to contain the analyte, and we're going to have 12.5 milliliters of 0.200 molar. So in this case, it's not truly an analyte because we know both the concentrations of the titrant and the analyte. But what we're going to be looking at is the pH. So that is what we are after here. So that is the experimental setup. What we're going to be doing is making small additions of sodium hydroxide, and we're going to be charting the progress as we go. So the first part of the question asks us to calculate the pH at the start of the titration, and we're going to write this point on the graph. So the first thing we need to know is that before any addition, we can take the pH of a strong acid by simply using its molarity, because we know that strong acids will dissociate and the concentration of H plus will be equivalent to the concentration of HNO3, which is 0.200 molar. When we take the negative log of the concentration, we will get the pH. So honestly, this first point, rather simple. The pH is 0.699. So on our graphs, go ahead and chart the point at 0.699, and that's going to be our first plotted point. Now, mine's not perfect, and I will try to follow along with you here, but there is our first point. Okay, the second point is going to come from calculating the pH of a solution after, we are adding 2.5 milliliters of our titrant NaOH. And then we're going to add this point to the graph. Now, we have added acid with a base. So this is a chemical reaction, which means we need a BCA table. Huge importance. So let's go ahead and work that out. If we're going to use a BCA table, though, you might also remember that we need moles of all of our substances. So we're going to calculate using our volume and concentration of our titrant to get 2.5 times 10 to the negative fourth moles of hydroxide. And we're going to do the same thing, but we have a 0.2 molar solution of our nitric acid. So we're going to go ahead and calculate 2.5 times 10 to the negative 3 moles of H plus. We're going to be able to use this in our BCA table. Now, I'm going to draw attention to the reaction. Remember, the net ionic equation for a strong acid with a strong base is just hydronium plus hydroxide yields H2O. That's it. So we're going to use that. And remember, this is for moles only. Initially, here are my molar values. Notice that water is not included. This will not affect the pH of the solution. Our change is going to come from identifying the limiting reagent. Hydroxide has a smaller amount, and this is our limiting reagent here. When we subtract, hydroxide will be eaten up completely. And doesn't that make sense? We had a strong acid to begin with, and we only added 2.5 milliliters of a strong base. So it makes sense that there's still H plus remaining in solution, which is why we have a low pH. We're going to take this value, and we're going to calculate the concentration. And remember, we only had moles, so we still have to divide by our total. I'm going to write that in, our total volume of our new solution. Remember, that's changing. So now we have a 0.15 molar solution of H plus. Now we can continue like normal, take the negative log of the H plus concentration to get pH, and look, it went up from 0.699 to 0.824. So we're going to go ahead and add a second plot point down here and to the right. So not a huge shocker, but we did increase a little bit, but it's not changing a whole lot yet. Let's continue. Okay, moving right along, what we're going to do in this next part is we're going to add more base, but instead of trying to figure out where we started from in the last point to this point, what we're going to assume is that we're starting fresh. So assume that we had no base added to begin with, and we are making a 5 milliliter addition from zero. Okay, we would drive ourselves crazy trying to figure out how much would go between and back and forth, and it just gets messy. So let's assume that we're starting from zero. So let's go ahead. We're going to calculate the same way. We have an acid-base reaction, so we're going to have to use a BCA table. And feel free at any point to pause this video so that you can get these notes written in. I know it takes a while. But instead of 2.5 times 10 to the negative fourth moles of hydroxide, now we have 5 times 10 to the negative fourth moles of hydroxide. Same amount of hydrogen. We're going to use the same net ionic equation, strong acid, strong base. We're going to plug in our mole values. Water is not included. So this is identical to the last one. We're just changing the amount of hydroxide we're adding. OH is still the limiting reactant because it's power of negative 4. We're going to go consume all of the hydroxide. We have a larger portion here that is removed from the hydrogen concentration. So once we have that, we're going to divide by our total volume. Now, I'm going to take a second here and talk about this. Now, our total volume has changed. Careful not to use the same total volume. We've added 5 mils, not 2.5. Here's our new concentration. Take the negative log, and we will get a pH. And here we go. It is increasing in pH, but still, we haven't even crossed the threshold for 1. So let's go ahead and plot all of our points, 0.699, 0.8, and then 0.942. As you can see, we are steadily going up this curve. Titrations take a long time. Patience is key as we're going through these curves. But once you get through them, you truly understand the curves really well. Okay, again, we're going to assume that we started from 0, but now we're going to add 25 milliliters of NaOH, and then we're going to add this point to the graph. So, again, acid plus base, this is a chemical reaction. We need a BCA table with moles. Again, pause the video if you really need to slow down to get all these notes in. Feel free to pause. When we get to this point, check it out. What we notice is that the moles of hydroxide and the moles of hydrogen are equal. We can still use a BCA table. Our net ionic equation is still the same for a strong acid, strong base. But what you notice is there is no limiting reagent. And so both of them go to 0, which means water is the only thing that's remaining here. And what we know is that water by itself does not affect the pH. So yes, this is our equivalence point. We have finally reached it. There's a huge jump. We know that at strong base, the pH of the equivalence point is always going to be 7.00, depending on sig figs, of course. So let's plot our points, 1, 2, 3. And if I may fix this, I think it was somewhere closer to here. That last one's going to go up to 7. Huge jump at the equivalence. So we've got this spike right here. We have reached equivalence. So knowing that we've reached the equivalence point, any extra addition of base is now going to continue to spike our pH above 7. And what we're going to notice is that there is now more hydroxide remaining. So let's see how that plays out here. We're going to calculate our moles of hydroxide and hydrogen, and you'll notice that now we have more hydroxide than we do H+. Our BCA table is going to be the same net ionic equation. We don't have to switch anything because this includes both hydrogen and hydroxide. We're going to include our mole ratios, and then now our limiting reagent has changed to hydrogen. So be careful. That's the new change. Hydrogen will be consumed, and now there is excess hydroxide. What we can do is now take the concentration and look at our total volume here. Now it is 0.0475. It's 35 milliliters plus the original 12.5. And then we're going to have to be careful, and I'm going to have you star this in your notes. We can't take the negative log of the H plus because this is hydroxide. So this is POH instead of pH. Take the negative log, that gives us the POH. And then we're going to do 14 minus the POH in order to get us a pH, which makes sense. that it's at 12.3. So if we're plotting 1, 2, 3, there's the spike at the equivalence, and now another big spike all the way up to 12. So just a couple more and we will be finished here. Okay, now we know that we are past the equivalence point. We're up at a pH of 12. Let's continue adding more. We're going to assume we're starting from 0. Let's add 50 milliliters of NaOH. Again, pause if you need to. I know we're moving fast. More moles of hydroxide have been added. Our BCA table is the same. Our hydrogen is still limiting because we're past the equivalence point now. We have even more excess hydroxide. We're going to calculate, keep in mind, our total solution volume is changing. And we're going to calculate the molarity. We can take the negative log to get POH, convert POH into pH, and we get 12.602. Now, we are starting to level out. Let's plot the points. 1, 2, 3, there's the equivalence. We went up to 12, and then now we're kind of leveling off again, and we're going to be stable there as we add more and more base. So what's happening, and this is typical for a strong acid, strong base reaction. Start at a low pH, and we will end at a very high pH. So let's go ahead and, if you will, take time to go back and let's sketch a curve for this. And I know this isn't perfect. So the first few points were actually below 1, so these few dots may be just slightly off. But either way, what we're going to see is that we have this super upright curve. And as we continue, then it sharply levels off this way. Strong acid, strong base curves are known for their steep equivalence points. And so if we're asking for the equivalence pH, we basically take halfway between the two uprights, and we'll find that pH in a rough amount. Now, we can use indicators and select a careful indicator. If they're asking for the equivalence volume, then what we need to do is locate the steepest portion of the curve and continue down, and we can find how much titrant, or in this case, our NaOH base, was needed to neutralize the solution. Okay, that is all for our first titration plot. In the next video, we're going to cover a weak acid and strong base curve, and then after that, we'll do a weak base strong acid curve. Hang in there, guys.